Continuing with our explanations of hypothesis testing, remember the last step in our series of steps of hypothesis testing? First, we made the statistical decision, reject or don't reject. And then we said, well, do we act on it or not? Well, there's a difference between something being statistically significant and being economically meaningful. And there's a few reasons for that. One of the reasons is transactions costs. If we've looked at a strategy and said, well, this does produce positive abnormal returns, they're greater than zero. So at least that's what our hypothesis tells us. We can't reject that they're greater than or equal to zero. But if there's transactions costs involved, those costs of trading, bid-ask spread, and commissions, may outweigh the possible benefits from the strategy, even though the benefits are positive and statistically significant. Another thing is, if the strategy involves buying and selling, there's some tax consequences, and they may wash out any gains you may make from the strategy. And also, even though we've rejected, say we're testing whether a strategy has positive abnormal returns. Okay, so our null is less than or equal to zero. And we find, well, we got pretty good statistical significance that this strategy does produce positive abnormal returns on average. But that doesn't mean it's without risk. If it's true because we've got a large data set that we could reject less than or equal to zero. But if the strategy only works 4 months out of 12, well, we've got some risk there. We've got a lot of uncertainty about how this strategy is going to perform. So we've got to take that into account when we're deciding whether we actually want to employ a strategy because we think it's going to generate economic profits for us. Our next LOS here talks about the p-value. Well, let's go through the formal definition and then kind of explain it a little. A p-value is the smallest value of significance at which the null can be rejected, or the probability of getting the test statistic by chance, even if the null is true. So those are both the same thing there. Okay? Now, if we do a test at the one-tailed test, 5% significance level, and we get out in that rejection region, all we're going to report is, yes, we can reject this at the 5% significance level. But remember our example where we had a test statistic of like 6.33, it was like way out here off the screen. Okay? There was more information there. Remember, our test was whether it was bigger than 1.96. And we'd say, yeah, we rejected it at the 5% level. I guess it was, 165 standard errors for the one-tail 5% significance test. So if we get a p-value, and based on our test statistic, we say, well, we wouldn't have gotten anything this large when the null is true. Only 2.14% of the time. So by looking at the p-value, it kind of tells us the strength of our results. Now, if our p-value is 2.14, we can reject it at the 5% significance level or the 3% significant level, but we can't reject it at the 1% significance level. Now let's look at some test statistics and some more examples of hypothesis tests. We want to test the mean of a normal population when the population variance is unknown. So the more conservative is to use the t-statistic. So we take our sample mean and the difference between the hypothesized sample mean and our actual sample mean. In the denominator, we've got our sample standard deviation S, but we're talking about a test of the mean. So we need to use the standard error and divide S by the square root of n, our sample size. Test of a mean of a normal population when population variance is known, we can use a z-statistic for sure. And in that case, we've got the population standard deviation there, but that's all. That's the only difference from what we saw for the t-statistic. Now the critical value is going to be different for the t-test than for the z-test, but in terms of the test statistic itself, it's just the same, except one has the sample standard deviation, and in the other, for whatever reason, we know the true standard deviation. So let's work through an example here. We're going to use the 5% significance level. We're going to test the hypothesis that a machine is producing gizmos with a mean length of 2.5 inches. So that's going to be our null hypothesis. The average gizmo length is 2.5 inches. So clearly it's a test involving the mean. So our sample mean is 2.49 inches. The question becomes at the 5.5% significance level, can we reject the null hypothesis that the mean length is 2.5 inches? Well, let's see. Our sample size is 49, and our population standard deviation is given to us as 0.21 inches. So we have a known population variance. We have a large sample size. So we're going to use a z-test, and since our null hypothesis is mean length is 2.5, we use a two-tailed test. We're going to reject if our test statistic, which is the sample mean length, is too far below or too far above our hypothesized mean of 2.5. So it's a two-tailed test with a 5% significance level. So our critical values are 1.96. 1.96 standard errors either side of the mean. That's our 95% confidence interval. We're going to reject at the 5% significance level if we're in either the lower tail or the upper tail, outside that 95% confidence interval. So that's our decision rule. If the test statistic is outside this range of critical values, we're going to reject the null that the mean is actually 2.5. So let's calculate our test statistic. Well, in the numerator, we've got the difference between our hypothesized mean and our sample mean, and it doesn't seem very big, 0.01. But whether it's big depends on how many standard errors we are away from 2.5. So our standard error is this standard deviation of the population, which was given to us, divided by the square root of n. So here's how many standard errors are we away from 2.5. Well, we're actually 3.33 standard errors below 2.5. And that's certainly outside our critical values of minus 1.96. So we're going to reject. We're outside the range of critical values, minus 1.96 to plus 1.96. We're clear down here at minus 3.33. And you can see that graphically represented here. Okay. Here's our 95% confidence interval, 1.96 standard errors either side of our hypothesized mean. Well, we're working with the difference between our sample mean and 2.5 now. So our hypothesis is really that that difference is 0. So let's look now at a one-tailed test. We're going to use the same data as the previous example, and we're going to test the hypothesis that the machine is producing gizmos with a mean length less than 2.5 inches at a 5% significance level. So our null hypothesis now, remember, it has to include the equal sign. So its mean is greater than or equal to 2.5. And our alternative hypothesis is that the mean is less than 2.5. So that's what makes this a one-tailed test. That alternative hypothesis isn't not equal to, so we can reject with a high or a low value. It's less than or equal to, and so we can only reject this null hypothesis greater than or equal to 2.5. Okay? If we get statistical significance below 2.5. So our critical values now, remember it's 5% significance still, but it's a one-tailed test. So to get 5% in that one tail, our confidence interval is going to be that 90%. Now we're going to ignore the upper tail. We're certainly not going to reject that the mean is greater than or equal to 2.5. Even if our mean was 3.5, we wouldn't reject that. We're only going to reject if we get a low value, statistically significant value below 2.5. So same test statistic, and we got minus 3.3. So now we're going to reject that mu is less than or equal to 250, because we have the 0 here, remember, because we're working with the difference between our sample mean, 2.49, and our hypothesized mean of 2.50. So we're in the rejection region in this one-tailed test as well. So what are we going to conclude? Well, we're going to reject that mu is greater than or equal to 250, and in favor of the alternative hypothesis that the mean is less than 2.5.